Today I'm going to be addressing a titration of a weak acid with a strong base. It's a classic chemistry problem, and we're going to be addressing in particular three stages that I really want you to focus on, at least initially, of a titration. Because if you master these three stages, it will be a lot easier for you to understand exactly what's going on. So what's a weak acid? A weak acid is something like CH3COOH, acetic acid. We're going to be looking at that in a little more detail. First, however, I want to focus on these three stages, which I call before, at, and after. Imagine initially in our before stage, you have your CH3COOH sitting around in a beaker. This is what we call the before stage. Our mnemonic here is BA, B-A-A. So if CH3COOH, a weak acid, is sitting there in aqueous solution, it's going to have a certain pH, and we can calculate that. However, in a titration, by definition, we keep adding strong base until we reach these various stages. So stage 2 is what I like to call at. At is the end point. What does the end point mean? That means all the weak acid is consumed. So that's our first A of Ba, if you will, at the end point. All the weak acid is consumed by the addition of strong base. Finally, in our third stage, we have after. After the end point is where you start to see a really drastic change in pH. This is because you have consumed all the weak acid, and all you're doing at this point is adding base, which is the main determinant of whatever your pH is going to be, because the solution is becoming very basic very quickly. Now, I've said there are three stages. The truth is, in a titration, there's an infinite number of stages, and there's also an important stage actually between before we start adding any strong base at all to our weak acid and the endpoint itself, which is when all the acid is consumed. In particular, for you future biochemists, we're going to focus on something called the midpoint. Keep in mind this is different from the endpoint, and it's the point when half the weak acid and only half is consumed by the addition of strong base. I'm going to be going through all this in some very gory detail, so if you're not understanding it yet, don't worry. This is just an introduction. We're going to be going over this not only in gory, but in minute detail. One point I want to make, however, is there's a lot of terminology here, and I just want you to keep in mind this endpoint is used interchangeably with a term called equivalence point. So if you hear either one of those, it means the same thing. The first thing we're going to address here is a classic weak acid strong base titration. If you are an aficionado of weak acid strong base titration problems, you are going to see again and again titration problems that involve CH3COOH, which is acetic acid, and acetic acid is the main ingredient in vinegar. So if you've ever made salad dressing, you have encountered acetic acid. Now, it just so happens that something like acetic acid as a weak acid can be titrated with a strong base, such as NaOH, and it will be ultimately neutralized because NaOH will react with the weak acid to consume it. Now, in terms of a classic problem, this that we see here is an example where we are taking 50 milliliters of 0.1 molar acetic acid. It has a specific Ka, and we're titrating it with 0.100 molarity NaOH. So we're asked in this problem to calculate the pH at three different stages. One is before we've added any base at all. The second is when we have reached this famous, or some might say infamous, equivalence point, when all the weak acid has been consumed by the reaction with strong base. And then we have this after period. So again, it's BAA or ba, like sheep. So if we actually go beyond the point where if we have consumed all of our weak acid, we start just adding strong base, pH goes up really fast. So these are the three different stages that we're initially going to do calculations for pH at each of these different stages. In the beginning, there was the before. What do I mean by the before? So imagine you're in the lab and you have this glorious titration setup that you see over here. And keep in mind that your CH3COOH is in your flask down here, and you're actually titrating with your strong base, NaOH. Now, you know, hopefully, that if you react NaOH with CH3COOH, you're going to get the conjugate base, acetate ion, and water. However, we haven't done anything yet. We're just saying you have a CH3COOH solution. It's sitting there in all its glory. You haven't added any strong base to it. What are you going to do? You're going to set up an ice chart that uses your initial starting concentration of your weak acid. And then you're going to do the usual ice chart procedure, which is figure out how much of this ionizes into CH3COO- and H+. We're going to need to work in molarity, and we're going to have to use Ka to set up our equilibrium expression. Once we've done our calculation, we can calculate our pH using the H+ at equilibrium. So let's take a look at exactly how we're going to do that. Here it is, the ice chart, our friend, the ice chart. Now, notice we have some information here. We're told that we have 50 ml of 0.1 molar acetic acid. We're given our Ka, and we're potentially going to titrate it with 0.1 molar NaOH. However, we have not added any base here, any strong base yet. No NaOH has been added to our beaker. Now, a common mistake here is for students to get worried about the fact that they have 50 ml of 1.1 molar acetic acid. In this case, the volume of solution doesn't actually matter. We're working in molarity, so all we really want to consider is that we have 0.100 molar CH3COOH, and that's going to dissociate to some extent into the acetate ion and the H+. And it's really the H+ that we care about, right? Because that's what's going to give us our pH. So this is the equation, and this is what we're after. Okay, so this is going to be minus x. Here we're going to end up with 0.100 molar minus x. This over here is going to be plus x and plus x. So this is going to be x, this is going to be x. Notice if we're going to figure out the hydrogen ion concentration, we need our equilibrium expression, and that is going to simplify to x squared over 0.100. I'm going to ignore this minus x. We're able to do an approximation here, equals 1.8 times 10 to the negative 5. So when we figure out what x is, I'll let you worry about the math here. But basically, we find out that x equals 0.001342, keeping a good number of significant figures here. And then I'm going to take the negative log of this number, right? Because that's what gives us pH. So basically, I've solved for x, right? As I said, you can do the math. Once we've solved for x, take the negative log. Why? Because x is the hydrogen ion concentration. And that's what we need to get pH. When we take the negative log of this number, we get a pH of 2.87, 3 sig figs. Okay, so that's before we have actually commenced our titration. This is the pH of our lone 0.1 molar acetic acid solution. Again, I remind you to ignore the 50 ml, just go with the molarity. It doesn't matter if we have 100 ml or 200 ml or 1,000 ml, the molarity is the molarity is the molarity. Now, we begin our titration. God saw that her titration setup was good, so she started to add strong base to her weak acid. You've all been there, I know. You have done this kind of setup where you have a weak acid in your beaker and you start adding strong base. So the question is, when are you going to get to the end point? Well, the end point simply means that you add enough strong base to the weak acid that you have gotten just to the point where all the weak acid is consumed. At this point, any addition of more strong base causes a color change. Why? Because you don't have any more weak acid. The more strong base you add, it starts reacting with the indicator, and that produces the color change. You only want to go a drop above, as you know from hard experience, this equivalence point, because you're trying to get a very precise estimation of how much acid you actually have in your beaker. The real question, however, if we want to do a calculation, is what does it mean if we have consumed all our weak acid? We're talking about equilibrium here. So when we've consumed all of our weak acid, the fact of the matter is we have generated a certain amount of conjugate base. Conjugate base, which is CH3COO-, will not sit around in solution. We have Le Chatelier to keep in mind, and we have equilibrium principles. So what's going to happen? CH3COO-, the conjugate base, is going to react with water. We call this the hydrolysis of water to reestablish equilibrium principles. Therefore, we must calculate pH from the hydrolysis of water by the conjugate weak base, which in this case is CH3COO-. Now, once you have done that, you're actually going to have to use Kb and the molarity of OH- to determine your pH. Are you completely confused at this point? Well, if you are, I don't blame you, because this is the most complicated calculation. However, we're going to go through it step by step, and I think you will see how this all works if you contemplate deeply and carefully what goes on. So here we are in this scenario at the equivalence point. Notice what's going on here. We started with 50 ml of 0.1 molar acetic acid. We have added at this point 50 ml of strong base. This is going to effectively neutralize all our weak acid. We're basically going to consume all of it by reacting it with NaOH. So let's think for a minute about how many moles we have. Well, if we have 50 ml, that's 0.05 liter, and volume times molarity gives us moles. So we have 0.1 molarity of our acetic acid. This is going to give us 0.05 mole of CH3COOH. Same thing is true for NaOH. We're adding 0.05 molarity NaOH. What's that calculation? Same thing, right? We're taking 50 ml or 0.05. Oh, I think I made a little mistake here. Let's just go back. Fortunately, I can erase. It's one of my many talents. This is actually 0.005 molarity. Excuse me, moles of CH3COOH. See, even your professor makes mistakes. 0.05 liters times 0.01 molarity gives us 0.005 moles of CH3COOH. Rinse and repeat for NaOH. 0.05 liters of NaOH times 0.1 molar gives also 0.005 mole of NaOH. Okay, now I know this seems like heresy, but I'm going to put moles into my ice chart for the moment. 0.005 mole of acetic acid, 0.005 mole of NaOH. What's our relevant equation here? CH3COOH plus NaOH yields what? The OH is going to grab hydrogen ion, so we're going to get CH3COO minus plus water, H2O. This is our equation. Think about it. Proton transfer. Okay, all of the NaOH is going to react with all the available CH3COOH. So guess what? This is all going to go away. Goodbye, NaOH. It was nice knowing you. And then all of our CH3COOH is going to go away. Are you feeling sad? 0, 0. That's all we're left with. Neutralization. Now we started on the right side of our equation here with nada. So this is going to be, it's the plus x principle, right? 0.005. This is going to be 0.005. But guess what? I don't actually care about water. It's a liquid. It's not going in our equilibrium expression. So I'm just going to ignore it. Okay, this means at the end we have 0.005 mole of acetate ion. As I pointed out in the previous slide, this is what I like to call an untenable situation. We cannot have the acetate ion in solution by itself. It's going to obey equilibrium principles to go back and form some CH3COOH. So equilibrium, Le Chatelier, our French friend, can be honored. Now, how can we, so now we actually need a second ice chart. You may have been wondering, why do we have two ice charts here? Well, now we're going to contemplate what is the molarity of our CH3COO minus, which is going to hydrolyze water. Notice our total volume here is 50 plus 50. So if this is mole of CH3COOH, we have to divide it by 0.1 liter because that's our total solution volume. When we do that, guess what? We're back to 0.05. Now I'm going to put this here, even though we have these mystery question marks here. So what do I mean by CH3COO minus hydrolyzing water? Well, it's going to react with water plus H2O to yield CH3COOH plus OH minus. Okay, this is basically grabbing, acetate ion is grabbing a proton from water, it's forming its conjugate acid, and it's generating OH minus. So up here in our ice chart, we can put CH3COO minus on the reactant side, and then we're going to have CH3COOH H plus H plus OH minus rather on the reactant side. This and this, right? So as usual, if we're starting from 0.05 molar CH3COO minus, we don't have any of the conjugate acid or the hydroxide ion as yet. Business as usual, minus X, plus X, plus X. Now I'm going to get rid of this because I need some room here. I'm going to try to get rid of this. Little freaking out my computer right now. Okay, so what is this going to be? Now, this is the worst calculation you'll ever have to do in your life, I promise. If Ka equals 1.8 times 10 to the negative fifth, Kb we can get at through the Kw of water. I remind you that if you divide 10 to the negative 14 by Ka, you get Kb. So what is Kb in this situation? I'm not going to show that work. I'm just going to tell you it equals 1 point, where is it? Help! I know I have it here somewhere. Ah, no, I lied. Oh, yes, I do. 2.78 times 10 to the negative 11. So guess what? This is 0.05 minus X. This is X. This is X. We can set this equal to X squared over 0.05. Once again, we're going to do our approximation, so we're going to ignore our X. We solve for X. Again, I'm going to let you do the math here because otherwise this will take too long. But basically, what is X going to equal? X is the OH minus concentration, right? So when we solve for X and we find out that it equals this number that I'm going to tell you, which is 5.27 times 10 to the negative 6. We can then take the negative log of that to get POH. Once we have POH, it's a short hop to get pH. So it turns out the negative log of this number, POH, equals 5.27. And that means if we subtract that from 14, we get a pH number that equals 8.72. This is our pH at the equivalence point. I grant you, it's a bit of a production to get here, but yes, you can. That needs to be your attitude. Just do this until you get it, because there is a very logical flow here, I promise you. And actually, once you get the hang of it, you might be surprised to find that it's actually sort of fun. What is up next? Up next is after the equivalence point.